Anatomy of a Synthetic Human. Welcome back to School of Soul. I'm Adeline Atlas, 11 times published author, and this is the Humanoid Era series, where you learn everything there is to know about the new species arriving. Today's video is a dissection, not metaphorically, but structurally. If we're going to coexist with humanoids in our workplaces, schools, hospitals, homes, and even personal lives, then we need to know exactly what they are made of. This isn't science fiction. It's material science, mechanical engineering, synthetic neuroarchitecture, and robotic anatomy. In short, what is a synthetic human made of, and how does its internal structure allow it to function in a world built for us? Let's begin with the skeletal system, the load-bearing frame. The humanoid body is modeled on human biomechanics, but built using vastly different materials. Instead of bone, most humanoid robots use a combination of titanium alloy, aluminum, and carbon fiber for their internal skeletons. Titanium offers superior strength-to-weight ratio and corrosion resistance, making it ideal for joint stress points such as knees, shoulders, and the cervical spine. Some lightweight models use plastic composite internal frames to reduce cost, but high-functioning humanoids are structured like aerospace machines, built for flexibility without sacrificing mechanical durability. Joint movement is achieved through motorized actuation systems. Unlike the fluid contractions of biological muscle, humanoids rely on electric actuators, hydraulic systems, or more recently, artificial muscle polymers to simulate motion. The most common configuration is rotary actuators, which generate joint torque, often controlled via feedback loops from motion sensors and torque sensors. These actuation units are placed strategically throughout the skeleton, at hips, knees, elbows, wrists, neck, and spine, to mirror the natural pivot points of human mobility. More advanced systems incorporate series elastic actuators, which add a layer of flexible resistance, allowing humanoids to perform smoother movements and absorb impacts. These are critical in mimicking the fluid gait and coordinated posture of a human. As the demand for lifelike motion increases, new research is focused on electroactive polymers, materials that contract or expand when voltage is applied, much like biological muscle tissue. This would allow synthetic limbs to move in a far more organic way without requiring bulky motors. Now to the outer shell, the skin. Unlike industrial robots, humanoids are designed to interact closely with humans. That means their skin must be soft, temperature-controlled, and responsive to touch. Most humanoid robots today use silicone rubber compounds or thermoplastic elastomers, materials that can be tinted, textured, and molded to resemble human skin. These materials provide elasticity, UV resistance, and tactile realism. Some are embedded with haptic sensors, allowing the humanoid to detect pressure, temperature, and texture. Newer models are being equipped with graphene-based skin overlays that provide touch sensitivity through electrical conductivity. These skins can detect finger contact, slaps, brushing, and even pulse strength. Combined with heating elements and thin film sensors, the humanoid skin can maintain a warm body temperature, offer realistic resistance to pressure, and feel when it's being touched, then transmit that data to its control system. Inside the torso, where human organs would be, humanoids house a dense cluster of modular components: battery packs, power management units, circuit systems, and cooling hardware. The central processor, often referred to as the humanoid's brain, is typically located in the cranial housing or upper thoracic cavity. This processor manages everything: balance, motion prediction, environmental mapping, emotional response generation, and real-time communication. It's not a brain in the organic sense, but it is a processing center with thousands of simultaneous input-output loops. Most humanoids run on multi-core AI chips capable of edge computing, meaning they don't require a constant internet connection to process commands. This is essential for safety, real-time reaction, and offline functionality. Companies like NVIDIA, Intel, and Tesla have designed custom chipsets optimized for humanoid function, handling everything from object recognition and voice parsing to behavioral simulation and memory retrieval. To power this complex system, humanoids rely on lithium-ion battery cores, supercapacitors, or in some research labs, hydrogen fuel cell miniaturization. The average humanoid can operate between 4 and 12 hours on a single charge, depending on its activity level and sensor engagement. More advanced prototypes include dynamic power routing, which redistributes energy depending on which subsystems are most active. For example, rerouting energy from the legs to the head when seated. Now to the sensory systems. One of the most important distinctions between humanoids and traditional robots is the presence of high-fidelity perception. Their eyes aren't glass orbs, they're multi-lens optical cameras, often equipped with LiDAR, infrared, and depth-sensing arrays. These cameras scan the environment in real time, building three-dimensional maps used for navigation, facial recognition, and object interaction. Visual systems are supported by simultaneous localization and mapping algorithms, SLAM, which allow humanoids to move through unfamiliar terrain while dynamically adjusting their route. This is what lets them walk through a crowded room, avoid obstacles, and track facial expressions. Audio input is handled through spatial microphone arrays, allowing directional hearing and voice triangulation. Combined with speech recognition software and natural language processing, humanoids can isolate a single voice in a noisy room, parse language with high accuracy, and respond using text-to-speech generators. More lifelike models even synchronize lip movement with spoken language in real time. Let's move to facial expression and communication. Humanoids that serve in social or caregiving roles often have animatronic facial systems, small motors embedded under the skin that control eye blinking, brow raising, cheek lifting, and lip curvature. While limited in nuance, these gestures dramatically increase perceived trust and relatability. To simulate emotion, humanoids use behavioral conditioning algorithms. For example, if a person expresses frustration, the system may recognize certain keywords, tone patterns, or facial indicators, then trigger a pre-coded emotional response, such as apologizing, softening tone, or changing body posture. This is not empathy, it is probabilistic reaction modeling, but for the average user, it often feels real. Internally, many humanoids are now equipped with thermal management systems. These allow the body to maintain stable internal temperatures, prevent overheating of processors, and provide outward warmth that mimics human skin. Some use liquid-cooled spinal channels, while others use fan-based venting systems embedded in the torso. These systems ensure that processors and battery cells don't overheat, even under extended use. One of the lesser-known features of synthetic anatomy is olfactory and chemical sensing. While still limited, some humanoids are being outfitted with air sampling devices and gas sensors to detect smoke, volatile organic compounds, or even changes in human body odor. These capabilities allow them to assist in safety tasks, medical monitoring, or responsive caregiving. As humanoids begin integrating into medical and domestic environments, their anatomy is expanding to include synthetic organ substitutes. These aren't organs in the biological sense, but modular systems that perform analogous functions. A lung may refer to an internal air filter. A stomach may house battery packs or chemical sensors. These design metaphors help engineers organize components spatially and conceptually to maintain anatomical balance. Some humanoids are even being developed with internal fluid reservoirs to simulate biological weight distribution and movement rhythm. Now, onto connectivity and diagnostics. Humanoids are equipped with real-time diagnostic feeds. These systems constantly monitor joint stress, software errors, power levels, and sensor calibration. In many cases, they are Wi-Fi or Bluetooth-enabled, allowing engineers or owners to receive live health reports or issue software patches. High-end models are linked to cloud-based cognition networks, which means their knowledge base is constantly updated. They can learn from experience, but also from centralized data pushed from developer servers. Finally, there is the question of identity systems. Humanoids use digital ID tokens, facial biometrics, and encrypted memory logs to track who they are, where they've been, and how they're authorized to interact. In multi-humanoid environments, such as hospitals, factories, or military installations, these ID systems prevent cross-command interference and establish role hierarchy. This is how a humanoid assigned to elder care knows not to accept logistics commands, and vice versa. To summarize, a synthetic human is not just a shell of wires. It is a system of specialized substructures, each one engineered to replicate, replace, or outperform the natural human equivalent. From titanium skeletons to responsive silicone skin, from electroactive joints to AI speech engines, from thermal veins to machine-simulated emotions, every layer of the humanoid body is designed to appear familiar, function dependably, and provoke trust. But the purpose of this trust is structural. It allows integration. The humanoid does not have internal consciousness. It has internal circuitry. It does not possess intuition. It possesses adaptive protocol. It doesn't need sleep, food, or meaning. It needs charging, calibration, and data flow. This is anatomy engineered not for life, but for placement. The humanoid body is a body of strategy, built to enter human domains without resistance, built to satisfy physical presence, and built to function in the exact spaces we have always called our own. And that's the reality we now face. The new human body is not biological. It is synthetic. And it is arriving, not in metaphor, but in form. Hi, I am Adeline Atlas, 11 times published author, and SOS, School of Soul has a brand new series, the AI and Future Technology series. Look, you know the world is changing. And no, it's not going back to normal. Normal is over, and what's coming next is beyond anything we were prepared for. The School of Soul, AI and Future Technology series includes 319 videos on 1. The Download Society, How Data Has Replaced Destiny. 2. Predictive Future. Your next moves aren't random, they're forecasted. 3. Social Credit Systems. The behavioral economy now governs access. 4. Hive Mind. Synthetic telepathy and collective algorithmic control. 5. Nanobots inside you. Medical, military, and programmable intrusions. 6. Grief Tech. AI-fueled digital resurrection and simulated comfort. 7. Uploading your mind, consciousness transfer, and data-based identity. 8. Deep fakes plus AI clones. The replication of reality and identity theft. 9. Quantum humans. The merger of biology with quantum systems. 10. Digital afterlife, where your data goes when you die. 11. Resurrection science, reviving life through synthetic methods. 12. Immortal science, the end of death as we know it. 13. Longevity science, gene editing, anti-aging, and bio-upgrades. 14. Designer babies, engineered perfection before birth. 15. Artificial wombs, birth decoupled from the female body. 16. 3D printing, printing organs, limbs, and even humans. 17. The humanoid era, the rise of synthetic beings among us. 18. Legacy humans, the slow phase-out of unmodified analog people. 19. Smart cities, algorithmic environments that watch and decide. 20. Cloud-based societies, citizenship without borders or bodies. 21. Hackable humans, emotion, memory, and behavior under code. 22. Biometric scanning, your body is your password and your prison. 23. Sex tech, intimacy reprogrammed by machines. 24. Extinction of gender, fluidity, deletion, and design of identity. Every topic is fully explored with real-world technologies, patents, case studies, ethical analysis, and future forecasts. These aren't someday discussions. This is already happening. Join the SOS School of Soul Vault to overstand the future before it's implemented on you.